So far in this topic we've talked a lot about the structure of the atom. In the last video we looked at atomic structure and what atomic number and mass number refer to. But what you might have noticed is that the mass number on the periodic table isn't always a whole number, and that doesn't quite make sense because we can only have whole numbers of protons or neutrons. This is where the idea of the relative atomic mass comes in. Not all atoms of an element are the same. In order for it to be the same element, it has to have the same number of protons. But it is really common to have atoms of an element that have different number of neutrons, and these are called isotopes. Here is the definition at the top of the slide. Let's look at an example of hydrogen. Hydrogen has three main isotopes. The first one is the one we're familiar with one proton and one electron, but no neutrons. The second one is called deuterium, although you don't need to know the name of that. And it's still got one proton and one electron, but now it has one neutron. So if you remember, the mass number is the number of protons plus the number of neutrons. So with the second isotope of hydrogen, the mass number is 2. There's a third isotope of hydrogen. This one's called tritium. It has one proton and one electron, but it has 2 neutrons, which makes its mass number 3. So you can see, for the same element, we can have different versions of the atom. As long as they have the same number of protons, it's still the same element. But if they have different numbers of neutrons, it gives the element different mass numbers, and that makes them isotopes of the element. The relative atomic mass is a measure that takes into account the mass numbers of all of the different isotopes of that element in the world, by taking into account the relative proportions of each of the isotopes of the element, which we call their relative abundance. Let's look at an example. If in this case we had a yellow atom and a purple atom, each of them isotopes of each other, the yellow has a mass of 10, and the purple has a mass of 20. If we had a 50-50 proportion of each, then half of them would be 10 and half of them would be 20, and so the mean mass would be 15. You can work this out in a couple of different ways, but it's unlikely that isotopes have an exactly 50-50 proportion. So let's take this example. 60% of the isotopes are yellow and 40% are purple. In a sample of 10, that would mean 6 of them are yellow and 4 of them are purple. Remember, yellow has a mass of 10 and purple has a mass of 20. So, if we want to find the average mass of all of the different atoms in that beaker or in that sample, we need to take a weighted mean, and this just means that we take into account the yellow ones more than the purple because we have more of them. So, using the simple example of the atoms in the beaker, 6 have a mass of 10, so 6 times 10, and 4 have a mass of 20, so 4 times 20. The total is 10, so we divide it by 10. That gives us a weighted mean of 14. If we do it using percentages, we say that 60% have a mass of 10, those are the yellow ones, and 40% have a mass of 20, those are the purple ones. We divide it by 100 because it's a percentage, and we again get the same answer, 14. So if we had 50-50 proportions of isotopes of this element, then the mean would be 15. But if it's 60-40, then the weighted mean is going to be closer to the mass of the atom, which has a higher abundance. This is what the equation for the relative atomic mass would look like. Don't worry if it looks a bit scary. All we're saying is that you take the mass of the isotope you have times by the abundance, which would be the percentage of that isotope, and you add up the same thing for all of the different isotopes and divide them by 100. Let's take a look at an example. Chlorine is commonly used as an example to calculate relative atomic mass. It has 2 main isotopes, the isotope that has a mass of 35 and the isotope that has a mass of 37. 75% of the atoms of chlorine have a mass of 35, and 25% of them have a mass of 37. So to plug these numbers into the formula, the relative atomic mass would be 35, the mass of the isotope, times by 75, its abundance, plus 37, the mass of the second isotope, times 25, its abundance, all over 100. That gives us a relative atomic mass of 35.5, which, if you check on the periodic table, is what you have for chlorine. Have a go yourself at calculating the relative atomic mass for sulfur. We have two different isotopes, sulfur-32, which has an abundance of 95%, and sulfur-34, which has an abundance of 5%. Have a go at calculating it yourself, pause the video, and in a couple of seconds I'll show the answer. So the relative atomic mass of sulfur will be 32 times by 95 plus 34 times by 5 all over 100, and that gives us a relative atomic mass of 32.1, which, if you check on the periodic table, is what you would expect for sulfur. Using the periodic table is a good way of checking whether you've got a relative atomic mass in the right ballpark. The other way of checking, which may not seem quite so obvious, is that your answer should always be a number in between the two masses you're given. So, for example, 32.1 is between 32 and 34. It can't be below or above it, otherwise it wouldn't be a mean. This concludes our video on relative atomic mass. Here are a few of the keywords we've looked at today. I hope you've enjoyed this video, and see you again soon at mygcsescience.com.